So section 6.1 is volumes using cross sections, and we're going to be using the limit definition of an integral, which is basically this delta epsilon definition right here for an integral, but you don't have to memorize it like you did the delta epsilon definition of a derivative. We're not going to be doing a whole lot with this. It's going to be driving what's going on behind the scenes. So if you'll recall from Cal 1, we learned that we could approximate the area under a curve simply by looking at a sum of a whole bunch of different rectangles and adding up the areas of all these rectangles by dividing area under a curve into these evenly spaced rectangles here. We're going to extend that concept from 2 dimensions now into 3 dimensions to calculate the volume of a solid. We know that we will get the exact area of the curve if we look at the limit as the width of the rectangle approaches 0. You remember looking at how to find the area under a curve using areas of rectangles? All right, so we're now going to extend this concept to find the volumes of a solid. And what we're going to do is, instead of looking at a rectangle, we're going to look at a slice of a cross section. And the width of this cross section is going to be our delta x. So to find the volume of some shape, what we're going to do is we're going to look at the surface area of this thin slice of the cross section, and then we multiply it by the height or the thickness. Does that make sense? And then if I took an infinite number of these cross sections across this object here and just looked at different slices all along the way, and I add up the surface areas of all those slices, what I would have then is the volume of this entire object. We look at the formula for the volume of a solid of an integrable cross-sectional area, A of x, from x equals a to b. It's going to be the integral that goes from a to b. So here's a on our picture and here's b. And if I wanted that volume, I would integrate over those bounds from a to b the cross-sectional area of that function. So we need to have an area of a cross-section that we can find the geometric shape for, so that we can add up all those areas. So whenever you're calculating the volume of a solid, the first thing you want to do is you want to sketch the solid and a typical cross section. All right, so once you have a picture of what's going on, then you can find a formula for that A of x, the cross-sectional area of a typical cross section, and then find your limits of integration, your bounds that you're going to use for the integral. And then we integrate using the fundamental theorem of calculus. So let's look at an example problem here. Example 1 says that a solid lies between planes perpendicular to the x-axis. Perpendicular means that they're 90 degrees to this x-axis, starting at x equals 0 all the way out to x equals 14. So I've labeled my axis here on the x-axis from 0 to 14. And my cross-sectional areas are going to be perpendicular to this x-axis. The cross sections are perpendicular to the x-axis on the interval from 0 to 14, and the shape is going to be a square where the diagonals run from the parabola y equals negative 2 square roots of x, that's this parabola down here, and y equals positive 2 square roots of x. So these are going to be the upper and the lower bounds for our cross section. Now when I look at this, if I turn this cross section and look at a flat surface, because here I'm just looking at the thin slice of that cross section, because the cross sections are going to be diagonals of the shape, that means that if I were to cut this little section right here out and blow it up, it would look like this, where I would have the diagonal extending from here to here, and the shape would be a square shape basically that looks like this. So we have a shape that looks like this, where this line right here represents the length of this diagonal. Now I did give you a hint. It says the area of a square in terms of its diagonal is found by taking d squared over 2. These diagonal cross sections, they're going to start out really, really small down here. It would look like this. I'd have a square like this at this end, and over here at the big end I would have the bigger square. So you see what's going on? So each one of these surface areas is going to be represented by this shape right here. This shaded region right here would be the surface area of the cross section. And the area of that cross section in terms of x here is going to be equal to this top function right here minus the bottom function. So the top of this right here would be this point up here on the graph, and the bottom would be this point down here on the graph. Now that comes in handy because I have the top function as being this function right here, and then this would be the bottom function. Actually, that's not the area, that's actually the length of the diagonal. So the diagonal is going to be equal to the top function minus the bottom function. So looking at the functions, that means that the diagonal is going to be equal to 2 square roots of x minus negative 2 square roots of x. That comes from the top minus the bottom. Do you see that? Now, if I distribute this negative, that gives me that the diagonal is going to be equal to 4 square roots of x. Because when you subtract a negative, it becomes positive, and 2 square roots of x plus 2 square roots of x gives us 4 square roots of x. So that's how I can write my diagonal. The area of the cross section is going to be found using this formula right here. So using that information now, I can say that the area of my cross section is going to be equal to d squared over 2. Well, that's going to be 4 square roots of x squared over 2. Now you can't cancel this 2 with this 4 until you square both of these terms because exponents distribute across a product. Do y'all recall that rule? So if you have a product of terms raised to a power, you can distribute that power across that product. So that means that our cross-sectional area is going to be equal to square the 4 and you get 16, square the square root of x and you get x, all over 2, and when I simplify that, that's going to give us 8x. So this is that cross-sectional area. So to find the volume then, we set up an integral so that our bounds are going to be along the x-axis, and then our cross-sectional area, and this comes from this formula up here, in case you forgot, that cross-sectional area is going to be equal to 8x, and then we're integrating with respect to x, dx. Whatever your variable of integration is, that tells you what axis you look at on your picture to determine the bounds for your integral. Any questions about that? The question was, this is supposed to be a bunch of squares, right? Yes, it is. This vertical red line right here represents the diagonal of just one of the cross sections. So if I were to draw this thing out and try and draw it in 3D, what it would end up looking like is something that would be parabolic, but the ends of it would have this shape where we would have these lines here looking like that, and this would be a cross section. So it would kind of be a bulleted shape, kind of like that, where it's a four-sided shape, but the lengths of the sides expand in the shape of this parabolic region right here. So we've set up the equation for the volume of the solid. Now in order to find the volume, we just evaluate this integral using the fundamental theorem of calculus. When we integrate 8x, we're going to get what? We add 1 to the exponent, and that's going to give us x squared. And then 8 divided by 2 is 4. And we evaluate this from 0 to 14. So then we would plug in our upper bound and then subtract our lower bound. And then just doing the arithmetic, this is going to give us 4 times 14 squared is 196 minus 0, so that's going to give us 784 square units. We weren't told what the length was, so we're just going to put units, not square. Cube, we're finding volume. This is going to be cubic units. So in order to find the volume of a solid, you need to sketch out a graph of what it's going to look like, figure out a formula as a function of x or y, depending on what you're going to be integrating with respect to, figure out a formula for the cross-sectional surface area, and then integrate over the bounds. And the bounds are determined by what your variable of integration is. So for this problem, that was x. Now we're not going to be doing a lot of problems where we use cross-sectional areas. We're going to be doing more problems with solids of revolution. And solids of revolution are nice because we end up with a two-dimensional shape that we are then going to revolve around a fixed axis. And when we revolve this two-dimensional shape around this fixed axis right here, we generate a three-dimensional shape, and all of these cross-sectional areas are going to be circular because we revolve this around a circle. And circles are easy. We know how to find the volume of a circle. If this were my problem and I wanted to find the volume, I would say that the volume is going to be the integral that goes from 0 to 4 of my cross-sectional area, and it's going to be a function of x with respect to x, because this area is going to be perpendicular to your axis of revolution. So if I'm revolving around the x-axis, that means that this representative rectangle here, when I revolve it, it generates a circle. And the radius of the circle is going to be the height of that rectangle. So my a of x here would be the equation for the surface area of a circle. So I would get this is going to be equal to the integral from 0 to 4, and the area of a circle is pi times your radius squared. Well, what is the radius? The radius is going to be the distance from your axis of revolution to the outside edge of that shape. So that would be our radius. And that's a vertical height of y, but what is y equal to? Y is equal to the square root of x. So that's going to be our radius squared, and our radius for this problem would be the square root of x squared. So when I set this integral up, I would have the integral from 0 to 4 of pi, and pi is a constant, so you can pull it out of that integral, and I would just get x dx. So I'm not going to take the time to go through this problem. I just wanted to explain to you how we set up the formula for finding volumes of solids of revolution. So in general, how we get the bounds, they're determined by the area of the shaded region. The bounds come from the shaded region, which is why I said it's important to draw a picture of what's going on, because it will help you see where your bounds are going to be. The shaded region under this curve, y equals the square root of x, that I'm going to revolve around the x-axis, that whole region is going to be revolved, generating this shape. The bounds come from the shaded region along the axis that you're integrating with respect to. So let me add that. The bounds come from the shaded region along the axis of the variable you're integrating with respect to. Here, we're integrating with respect to x because we have a dx here. Our bounds were the numbers along the x-axis, not the y-axis. Does that make sense? So when I look at the solids of revolution using a disk method, a disk is a solid shape. So the disk would look something like this. When I look at that cross-sectional area, it ends up being kind of this shape, where the radius is going to be the distance from this axis of revolution, and we generate this thing that looks like a wheel. The thickness of this is going to be along either the x-axis or the y-axis. For the disk method, we want to draw in our two-dimensional picture what I call this representative rectangle right here. That tells us what our radius is. That rectangle will always be perpendicular to the axis of revolution if you're generating a solid shape whenever you're revolving. So for the disk method, your representative rectangle will always be perpendicular to the axis of revolution. So once you know what you're revolving around, you know that your rectangle that you're going to draw to help you figure out what your radius is going to be perpendicular to that axis. Since we're generating a circle, the area of a circle is pi r squared, where if you're revolving around the x-axis, this radius is going to be a function of x. So if you're revolving around the y-axis, it would be a function of y. So let's look at another example problem. In this problem, we're asked to find the volume of the solid generated by revolving the region bounded by y equals 4x squared, which is this function right here, y equals 4x squared, y equals 0, which is the x-axis, and x equals 3 about the x-axis. So x equals 3 is this line right here. So I've got the region that we've got bounded between these three functions, 1, 2, 3. I've got this region shaded gray already. We want to revolve it around the x-axis, so there's my axis of revolution. So when I draw my representative rectangle to help me determine what my radius is going to be, it's going to be perpendicular to that axis of revolution. So you would end up with a shape that looks something like this, where that axis of revolution would be in the middle. All right, so do you have in your mind now a picture of what this is going to look like when I revolve this? So to set up the integral, I know that I'm going to have this representative rectangle right here, and that's going to be the height. I know when I revolve this, I end up with a disk or a circular shape. So the bounds for my integral to get the volume will come along the x-axis. Well, the shaded region starts at 0 and it ends at 3 along the x-axis. So my integral is going to go from 0 to 3. And then I have the formula for the area of a circle, which is pi r squared. So that's going to be pi times what is my radius? Well, the height of this rectangle is your radius. How do you get the height? Well, the height would be the top function, which is this function right here, minus the bottom function. It's that y distance. So here we get y equals 4x squared minus y equals 0. So that's just going to be 4x squared. And I'm going to be integrating this with respect to x because x is my variable of integration. Any questions about where any of those parts came from? The height of this rectangle is going to be the top of the function minus the bottom of the function. The top of the rectangle minus the bottom. Well, the y value anywhere along this shaded region can be found by using this function right here because that's the curve that gives us the top of this shaded region. To get your radius, if you're integrating with respect to x, you're going to have a vertical line. The radius is going to be the top of the function minus the bottom of the function. So the top of the function in this case is 4x squared, and the bottom of the function is this value right here, 0. So we said that that was 4x squared. Does that make sense? So this is where this came from for our radius. And the formula for the surface area of a circle is area is equal to pi r squared. So I squared that radius. So now I need to take care of the arithmetic. Remember, we have to distribute this power across both of these terms. So that's going to give us the integral from 0 to 3. And I'm going to go ahead and pull the pi out of 16 because I got to square the 4. And when I square the x squared, I get x to the 4th dx. So when I integrate this, I still have my pi here. And then I have a 16. I could pull the 16 out as well. And when I integrate x to the 4th, I get 1/5 x to the 5th. And we evaluate this from 0 to 3. That's going to give me 16 pi over 5 times 3 to the 5th minus 0 to the 5th. So that's going to be 16 pi over 5 times what's 3 to the 5th? This is why God gave us calculators. 243. Now, 5 won't go into either 16 or 243, so when you write your final answer, I want the exact answer, and that would be 3888 pi over 5. So that would be your final answer. I don't want a decimal approximation. I want the exact answer. This is the exact answer. Moving on, example 3. Here we're asked to find the volume of the solid generated by revolving the region about the given line. The region in the first quadrant bounded above by the line y equals 2. So here's the line y equals 2. So that's bounding the top of our shaded region. Below by the curve y equals 2 sine x. So this would be the curve y equals 2 sine x. And we're going from x equals 0 to pi over 2. So this point right here would be pi over 2. So that means that our shaded region is going to be this region in the first quadrant, bounded above by the red line and below by the blue line. And this goes out to pi over 2. Because sine pi over 2 is equal to 1. 2 times 1 is 2, and here's the line y equals 2. That means that this point of intersection between these curves is going to be at pi over 2, 2. We're going to revolve this about the line y equals 2. So now we're revolving around this line. We are revolving this shaded region. Our representative rectangle is going to be perpendicular to that axis of revolution, and the thickness is going to be a delta x. So when I set up my integral for the volume, I'm going to have an integral that goes from 0 to pi over 2 of pi r squared. My radius here is going to be the top function, which is 2, minus the bottom function, which is 2 sine x. And I'm integrating with respect to x, so we put a dx. Is everybody okay with how we got the radius? The radius, remember, is the top function minus the bottom function. It's the length right here. That's our radius. So the top function we said was the constant function 2. The bottom function is 2 times sine x. And then the volume of the circle is pi r squared, so I need to square this as well. Now, when I square a binomial term, I can't just distribute the square across. I have to FOIL this out. So another way of writing this would be, actually the arithmetic would be easier if we go ahead and factor a 2 out. That would make the numbers smaller. So let's go ahead and rewrite this function. Rewrite your integrand as pi times the integral from 0 to pi over 2 of, I can factor a 2 out of this, and that would give me 1 minus sine x, and then that whole thing is squared. Now I can distribute that power across to the 2 and the binomial expression. And when I do that, that's going to give me 4 times 1 minus sine x squared dx. So the 4 can come out of my integral. So this would now be 4 pi times the integral from 0 to pi over 2 of 1 minus sine x times 1 minus sine x dx. And to simplify this integrand, what do we need to do? The question was, how did I turn the 2 sine x into 1 minus sine x? Both of these factors had a common 2, so I pulled that common factor of 2 out. And then what I did was I distributed the exponent to the 2 and to the 1 minus sine x, so the 2 squared became 4, and then that left me the 1 minus sine x squared. And when you square something, what you're doing is you're multiplying it by itself. So in order to simplify this, we need to FOIL out that expression in the integrand. So I'm going to move over here to give me some more room, and this is going to be 4 pi times the integral from 0 to pi over 2 of 1 minus 2 sine x plus sine squared x dx. I can integrate 1. I can integrate sine. I can't integrate sine squared. So in order to integrate sine squared, we're going to have to use what's called a power reducing formula from trig. You will have access to your trig formula sheets to help you with these trig identities, but this is one that we're going to use often enough. It is worth memorizing. So let me just write down the power reducing formulas for both sine and cosine. So if I had sine squared alpha, I could rewrite that as 1/2 times 1 minus cosine 2 alpha. And if I had cosine squared alpha, that's equal to 1/2 times 1 plus cosine 2 alpha. These are worth memorizing because they come in often enough. So I'm going to rewrite this sine squared alpha using this power reducing formula. So that's going to give us 4 pi times the integral from 0 to pi over 2 of 1 minus 2 sine x plus 1/2 times 1 minus cosine 2x dx. Now what I need to do is distribute this 1/2 across here, and then I've got like terms that I can combine. Really what we're doing right now is algebra, and algebra is the hardest part of calculus, remembering all the algebra rules. So this is going to be 4 pi times the integral from 0 to pi over 2 of 1 minus 2 sine x plus 1/2 minus 1/2 cosine 2x dx. Now you can see your like terms that you have. I have a 1/2, I have a 1, and a 1/2 that I can combine. So that's going to give me this integral. That's 4 pi times the integral from 0 to pi over 2 of 1 plus 1/2 is 3/2 minus 2 sine x minus 1/2 cosine 2x. And now you can distribute this or break this into 3 different problems or just integrate them all at once. I'm going to integrate them all at once. So we keep our constant of 4 pi. And when you integrate 3/2, what do you get? 3/2 x. And what do we get when we integrate sine? Negative cosine. minus 1/2. And what do you get when you integrate cosine 2x? You get 1/2 sine x, and that goes from 0 to pi over 2. Let me pause for a minute. I'm not going to pause the video, and I want to break away and show you how we got the integral right here. So this is some scratch work that you can do. So if you have the integral of cosine 2x and you want to integrate this and you don't know what to do, you can always do a u substitution. Let's let u be equal to 2x. So what is du equal to? It's 2 dx. I have a dx, not a 2 dx, so I'm going to divide that 2 off of the right hand side, and that gives me 1/2 du equals dx. So now I can rewrite this integral as 1/2 cosine u du. And when I integrate that, that gives me 1/2 sine u. I'd put plus c because this is just scratch work for this. And then you don't want to leave your answer in terms of u. You would get 1/2 sine 2x because that's what u was equal to, plus c. One thing I want to point out here is when we did this problem, whatever the constant is that x is being multiplied, if you put the reciprocal out in front, it saves you these steps from going through and doing the u substitution all the time because it works out this way all the time. If you have a constant times x as your angle on a trig function when you're integrating it, just go ahead and integrate it, leaving the angle alone, but multiply by the reciprocal of that constant. That's how you get this term right here. The half is a constant that's pulled out. When we integrate cosine 2x, that gives us 1/2 sine 2x. This should be a 2x right here. All right, so now we use the fundamental theorem of calculus, and we're going to plug in our numbers. So this is going to give us 4 pi times, plug in your upper bound, and you're going to get 3/2 times pi over 2 plus 2, because I've got to distribute that negative right there, plus 2 cosine pi over 2 minus 1/4 sine, and then 2 times pi over 2 ends up being pi, doesn't it? Minus, plug in our lower bound, that's 3/2 times 0 plus 2 cosine 0 minus 1/4 sine 0. Now we evaluate the trig functions. Cosine pi over 2 is 1, sine pi is 0, cosine 0 is 1, and sine 0 is 0. So that'll help us clean up the arithmetic. And that's going to give us 4 pi times 3/2 times pi over 2 ends up being 3 pi over 4 plus 2 times 1 is 2. This term goes to 0. Minus, that term goes to 0, minus 2 times 1 is 2, and then plus 1/4. That's not right either. Hang on, wait. I'm missing something somewhere. Duh. Cosine pi over 2 is not 1. Cosine pi over 2 is 0. Cosine 0 is 1. Got it. Okay, so that term goes away. We don't need that term right there. All right, so since cosine pi over 2 is 0, we end up getting 4 pi times 3 pi over 4 plus 0 minus 0 and then minus 2. So this should be a minus 2 right here. Now it's looking like it's supposed to look. And then when we distribute this pi over 4 across, that's going to give us, the 4's are going to cancel out. That would be 3 pi squared minus 8 pi. And that would be our final answer. And we weren't given units, so these would be cubic units, whatever those units happen to be. Took a while to get there. And notice it wasn't the calculus that was hard. It's the algebra and the trig and stuff that's little things that can trip you up. The calculus in and of itself is not that hard. Now, because these problems are time consuming whenever you start them at the beginning and work all the way through, when you take your test in class, it's a pencil and paper test. Oftentimes I'll just have you set up the integral so that I know that you understand the calculus just to save time, and I can test more concepts that way. But on your homework, I want you to go ahead and work these out to the end, because you will have some problems on your test that will need to be worked out all the way to the end. Our second exam is going to be focusing more on more complicated integration techniques. This wasn't anything that was terribly complex, other than we had to recognize how to use the power reducing formula, and then if you needed to do the scratch work to take care of integrating the multiple angles there. All right, next we want to find the volume of the solid generated by revolving the region bounded by these curves about the y-axis. So the first thing that you need to do is sketch a graph. We have x equals 2y squared. So now I've got x as a function of y, not y as a function of x. So we need to sketch a graph of this. This parabola is going to start at 0, 0, and so it's going to look something like this. X equals 2y squared. X equals 0 is this point right here, y equals -9, and y equals 9. Well, if y is equal to -9, what is x going to be? Well, -9 squared is 81. 81 times 2 is way far out there. So we're going to call this point out here. So this is the line y equals 9, and this is the line y equals -9. So the solid is going to be formed by revolving the region bounded by this blue curve here. X equals 0 is the y-axis, y equals -9, and y equals 9. So my shaded region ends up being this region right here. I have symmetry now because of this as well. So these points are going to be at 162, 9 and 162, -9. Those are going to be our bounds. We're revolving this about the y-axis, which means that our rectangle, our representative rectangle, needs to be perpendicular to that axis of revolution. This thickness of this rectangle ends up being a delta y, which means that our variable of integration for this problem is going to be y. When I revolve this shape about the y-axis, I end up with a shape that looks something like, so I have a three-dimensional object that looks something like that, where this would be the top of it. Now, because of symmetry, the volume of this top half is going to be exactly equal to the volume of the bottom half, isn't it? So what I could do is just use this top function to integrate, because this volume is going to be equal to this volume, isn't it? So when I set up my formula for my integral, I'm going to say that the volume is going to be 2 times the integral from where to where. What will be my bounds on my integral? Does it go from 0 to 162 or 0 to 9? 0 to 9. The 2 is here because I'm doubling that volume. Instead of integrating from -9 to 9, I'm going to integrate from 0 to 9 because the shapes are exactly the same. So I'm just going to double that and have a 0 in my integral, which makes the arithmetic much easier. So then the cross-sectional area is going to be this circular shape right here, this circular disc, and the area of a circle is pi times the radius squared. What's the radius? Well, the radius is this distance of this line right here. And that's found by taking the right-hand function minus the left-hand function. If you have a vertical radius, it's top minus bottom. But for this problem, when we have a horizontal radius, we use the right-hand function minus the left-hand function. The right-hand function is this curve right here. The left-hand function is 0. So this ends up being 2y squared dy. So when we clean this up, that's going to give us 2 pi times the integral from 0 to 9 of what? Square the 2, square the y squared, and you get 4y to the 4th dy. So I'm going to go ahead and pull that 4 out, and that'll make this 8 pi times the integral from 0 to 9 of y to the 4th dy. What do you get when you integrate y to the 4th? 1/5 y to the 5th. And this is bound from 0 to 9. So this is why God gave us calculators. So this is going to be 8 pi times, actually I'm going to pull that 1/5 out and make it 8 pi over 5, and this is going to be 9 to the 5th. This is, plug in your bound and you get 0 to the 5th. Thank you. It's your upper bound, 9 to the 5th, minus your lower bound, 0 to the 5th. So when you plug in your bounds, you get 9 to the 5th minus 0 to the 5th. Use your calculator to handle the arithmetic, and that's going to give you 94,478.4 pi. What do we do if we have a hollow shape? Well, if we have a hollow shape that we're revolving around the axis of revolution, you'll be able to tell when you sketch your picture because not all of the shaded region will be touching this axis of revolution. When we revolve this shape that's floating above our axis of revolution, it generates a hole in the middle of our solid. Up here, we were revolving solid shapes because our shaded region touched the axis of revolution everywhere, and so that generated a solid shape if this axis touches, the shaded region touches the axis of revolution. But down here, our axis of revolution, it doesn't have any shaded region touching it. And so when we revolve this shaded region, we end up with a shape that has a hole inside. Well, that generates what's called a washer. And if you look at this shape right here, you see that it's a washer shape. And the way we would find the area of a donut, basically, we would have two radiuses, or radii. We would have an inner radius that's smaller, so we'll use a lowercase r, and an outer radius that's larger, so we would use the uppercase r. And that area of that washer is going to be pi times, it's going to be the outer circle, pi r squared, minus the inner circle, pi times a little radius squared. Well, I have a common factor of pi that I can factor out, and that just means we're going to be looking at the outer radius squared minus the inner radius squared to get this surface area of this shape, this cross-sectional shape right here. So before, when we had a solid shape using the disk method, we just used area equals pi r squared. Now we're using area equals pi times the outer radius squared minus the inner radius squared. So we have an outer radius and an inner radius. The washer's area then is going to be equal to pi times the outer radius squared minus the inner radius squared. So in this example, we want to use the washer method to find the volume of the solid generated by revolving the shaded region about the x-axis. We can once again use symmetry. We're revolving around the x-axis, which is this axis right here. The graph on the left, this region right here on the left, is the same as the region on the right. So what I'm going to do is I'm going to double my integral and just use the positive numbers. So this area is going to be the same as this area. So when I set up my integral for my volume, I'm going to double that integral that goes from 0 to pi over 2. So when I revolve this around the x-axis, my representative rectangle is going to be this distance right here. Looking at that, I need to determine what is my outer radius and what is my inner radius. Well, the outer radius is going to go from here to here. It's that constant because it stays the same as x moves along from 0 to pi over 2. The inner radius is going to be the distance that goes from here. So the outer radius is going to be this top function, y equals 2. The inner radius is going to be this inside blue function, y equals 2 square roots of cosine x. So when I set up my integral, I've got 2 times, because I'm doubling the volume, pi r squared. Well, my radius, though, is going to be the outer radius squared minus the inner radius squared, and I'm integrating with respect to x. My bounds are found along the x-axis here. Does that make sense? Where did this 2 come from? Because I'm doubling the volume. I'm only finding the volume for half of this shape because of symmetry. Where did this 2 come from? From the y equals 2. It's that distance from the axis of revolution to the outside edge of your shaded region. And then this is the inner radius. It's the distance from the axis of revolution to the inside edge of my shaded region. So then I can clean this up, and that's going to give us 2 pi times the integral from 0 to pi over 2 of 4 minus 4 cosine x dx. And you can factor a 4 out if you want. It might make the arithmetic easier. And then this would be 1 minus cosine x dx. And when we integrate that, what are we going to get? X minus sine x, the integral of cosine is sine. And then we're going and evaluating this from 0 to pi over 2. So we're going to plug in our bounds. And that's going to give us 8 pi times pi over 2 minus sine pi over 2 minus 0 minus sine 0. So sine pi over 2 is 1, sine 0 is 0, and that's going to give us 8 pi times pi over 2 minus 1. If we were to distribute that 8 pi across, that would give us 4 pi squared minus 8 pi, and that would be your final answer. Okay, so we've seen several examples of how to find volumes of solids of revolution using both the disk method and the washer method, so I'm going to cut this off, stop the video for this, and we're going to take a short break before we continue.